Hi, my name is Ahmed Salam. I'm gonna present today AdaCompression, adaptive compression for online computer vision services. This paper discusses how to compress an image in an adaptive way, considering that you can still inference the compressed image by using an EDNN model that is available on cloud-based computer vision services, while still achieving the same average accuracy. The compressed image will be still understandable by human vision system as they still use a standard reconfigurable way of compression called JPEG codec. The table of content of this presentation will include background, and I will talk a little bit about JPEG baseline, then the challenges of this research, and then I will talk briefly about reinforcement learning and the contributions of this paper, and the problem formulation, and then the DRL agent design, and the results and insights about their design, and then some critiques. With the great success of deep learning in computer vision, this decade has witnessed an explosion of deep learning based computer vision applications. As well known in the literature, there are two main image processing problems: image classification and object recognition. Both of them depend on the image representation of the source image. One of the known datasets is ImageNet, which is represented using the JPEG codec. Because of the huge computational resources consumption of deep learning applications, like for example inferring an image for image classification problem on a JPEG on a VGG19 model, it would requires around 20 giga floating point operations per second for a GPU resource. Nowadays, the sources of images are a lot, where some services require real-time operations, real-time inferring, like action recognition application, or even image classification. Many of the available edge devices are provided with many sensors with explosive amount of data to be uploaded to a certain server to have a certain operation. As this edge device have a limited computational resources, cloud-based computer vision services are used to hold all the required computational power. These devices are required to upload the input image to the central cloud service providers like Google Vision or SenseTime as well known now. This leads to a significant uploading traffic burden, and it requires to compress it before uploading it. As I mentioned before, the most known codec in the literature is the JPEG codec, and known as a lossy type, which it adds some distortion to the input image. The conventional way of compression is to select a fixed JPEG configuration to the pipeline and generalize over all the input image. Then it is uploaded to the cloud-based computer vision model. These models act as a black box to the end users, and it receives a distorted image from the lossy codec. This compression will not be sufficient for deep computer vision models in performance, but it will only optimize for human vision. It is only optimized for human vision systems. The compression of an input image will introduce some distortion level that would change the information content of an image to be misclassified, but maybe another distortion level would help decrease the inferring losses, which mean increasing the accuracy. So the important question here is that we should ask ourselves, can we improve the JPEG configuration adaptively for different cloud computer vision services without any pre-knowledge of the original model and dataset? This is a challenge that we have in this paper. In this slide, I would explain briefly idea about the baseline of JPEG coding. The input image will be divided into 8 by 8 blocks, and then DCT transformation will be applied to reorganize the coefficients from low frequency to high frequency. As well known in to human vision system that it is more sensitive for low frequency than the high frequency. Then the next stage, which is called the quantization, will take care about removing some of the high frequency components. So what does it mean? What does it mean by quantization? Quantization is the process of mapping input values from large set, often in a communication continuous. It's a continuous set to output values in a countable as accountable values like like a smaller set. So the quantization limits the number of steps of high frequencies coefficients as they are less sensitive to the human visual system, and keep more levels for the low frequency components. After getting the smaller set from a large set, we do entropy encoding, and this entropy encoding, it's just to take care about to give small number of bits for the high probable coefficients and large number of bits for rare coefficients. Both the DCT stage and the entropy encoding are lossless, but the quantization is lossy. What does it mean of lossy? Lossy, it means it is irreversible. It is irreversible operation. This stage can be generated using different quantization tables, like this one. As you can see here, the quantization going here from low frequency component to the high frequency component, and the numbers getting larger when we reach the high frequency component. So as you can see here, the quantization table is saved in integer values. So when I quantize and then round the result, so each quantization table is defined by something called quality factor, which it has a range of QF5 until 100. 100, it means that the input image will not be quantized like the same quality as the input. Not as this one as shown in the slide, where the inputs one is quantized. As we can see here, there is like a lot of artifacts appeared in the output image. But if we decrease the quality as shown here, the size of the image will be decreased, which is preferable to decrease the burden on the traffic to upload the image. And this quantization table have been designed based on the human vision system. So the human can detect the output, as we can see here from the input image and output image, but the deep learning models might not be sufficient for deep learning models, and it changes the image context of the information context of an image. In this slide, I will introduce some challenges that this paper has handled. So first point, lack of information about the cloud computer vision models. Where different studies in which the computer vision models are available, so one can adjust the JPEG configurations according to the model structure or retrain the parameters in it. One way to do this by greatly search a gradient descent to reach an optimum compression level in JPEG, and I think this will not be efficient as we will have a multiple compression levels for each image, which will be very exhaustive to search. Second challenge, different cloud computer vision models need different JPEG configurations, where the target to provide a solution that is adaptive to different cloud computer vision services by generating configuration for different models. The third challenge is lack of well-labeled training sets. What I mean with well-labeled, it means like which image correspond to which quality factor. So like for example, image that will have only like one quality factor with by average 95 QF. Here is I'll introduce some examples for different quality factors for input images that can show us some motivation that decreasing the image size might not affect some examples, but it will affect others according to the textures in the image content. As we can see here, it's the different cloud service, which is Face++. The first image is quantized by quality factor 75, and the second image is quantized by quality factor 55. Where the first image is classified as donut, by the second one it was not classified as donut, so it's a failed to recognize. The second image is quantized by 75 and the same quality factor was applied. The first one, both of them are the second one is failed to recognize. And in the third one, the quality factor was 75, and the second one was quality factor 5, and it is the same label. So it's passed. As we can see here, the first two images are virtually similar for human beings, but for deep learning models give different inference results, only because they are compressed at a different quality factor from 75 to 55. But here in the third image, it's highly compressed and looks distorted compared to the first one. But the deep learning model can still recognize it. So in some cases, prediction performance does not care about image qualities. In this slide, we show the proposed pipeline that rely on reinforcement learning mechanism. As you can see here, the difference between this figure and this figure is the adaptive way of configuring the shaping. And here we are just choosing one configuration for all the cloud services, but here we choose the configuration for different cloud services. Here I will mention how the reinforcement learning working in our algorithm. So as we know that any reinforcement learning mechanism has two main things. It's agent and environment. In our application, the agent will be the JPEG, and the environment will be the cloud, the cloud computer vision service. So the environment will choose randomly a state which is a quality factor, for example, in the range of 5 to 100, and tells the agent to compress this image. Then an action will be taken, by compressing the image and then uploading it to the environment, to these three main cloud services. Then a reward function will be there in the environment, and it will be function in size and accuracy, and then it give it back to the agent, because the agent here is the one who is responsible for choosing the right decision for which action it should select. Which action in terms of in which input image I should select which compression level or which quantization factor. So after I'm sending a reward, the environment will choose another quality factor after it already sent the reward. So it will be another quantization factor in the same range, but it would be different from the. This happens during the training stage, like the environment select a random quality factor and send it to the agent. So it's like exploring and exploiting. Then after the agent it will train, it will take always an action. So without sending any reward, or the environment will select any states, as it will be already trained and know how to select any compression, any quality factor, the previous one. So their contribution here mainly summarized in these 5 points. So they have created interactive training environments that can be applied to different computer vision cloud service at different times. DeepQ neural network agent is proposed to evaluate and predict the performance of a compression level on an input image. Reward function is based on accuracy, as we mentioned before, and data size to train the DeepQ network. The DeepQ network is the one who represents the agents that will choose which quality factor to send to the environment, which is the cloud service. And inference and estimation retraining, which in the RL community called exploring and exploiting mechanism, is designed to restart the training procedures once the sensory changes, because in some images you will have a view for an open area, or have a view of an object in an indoor area. So we have to make our algorithm adaptive for these different views. Analysis and insight will be shown in this presentation by showing different patterns provided using GradCam to explain why the Q network chooses a specific compression level, which mean also like quantization factor. Here is I'm gonna present the proper formulation. So they denoted the cloud deep learning service as y reference equal m of x reference. For all input, x reference will belong to x capital, which is the data set, and y reference here is for the predicted ground truth labels for each input image. And for YC, it will be also the predicted labels, but for an input of x of c that is compressed at c level. And they have generalized the accuracy metric AC by comparing the Y reference with YC To be more general, they only use the top 5 score for comparing between the Y reference and YC. They only want to keep the top 5 accuracy, and this is logic to keep the model some way relaxed. And they minimize over J for the distance. They use Hamming distance, which it will be only 1 when x equal y, and otherwise it will be 0. Here is a DRL agent design. The main goal is giving a proper compression level that minimizes the file size, which is denoted by SC, while keeping the accuracy the same. So what we will have, it's an input features, which is input image is a continuous numerical vectors. So the output is expected to be will be discrete quality level, which is C. So the naive way to design deep Q neural network have some challenges, as in this application the state space of the reinforcement learning is too large and preserve enough details. We have to add many layers and nodes to the neural network, making the DRL agent extremely difficult to converge. And it will take, of course, a long time to train. Each step in a large inference neural network, making the training process too time consuming. And the DRL agent starts from random trials and starts learning after it found a better reward feedback. So to solve this problem, they have to use like a pre-trained things that understand the image to get instead of using the deep Q network, or in another form of a deep Q network. So what they have used is a pre-trained small neural network to extract features from the input image to reduce the input dimensions and accelerate the training process. They use the early layers only of the MobileNet version 2. Why MobileNet? Because it's very light to be loaded on one of the edge devices. As you can see here, I was curious why they have used such a model like this. So I run the trials and I took a random sample from ImageNet and the quality factor of 90, and then I plotted the feature maps. So I found the output of the feature maps explicitly saves the dog itself. At least the dog is still there, but even like there's it's more obvious than the background. So that's made me understand why they have choose MobileNet. This is a pipeline of the DRL agent. So here we have the edge device, and here is we have the network edge. So what we have here is the input image, and then the deep Q network that decide which compression level we select, and then we get the compression degree and then the input image and compress the image, and then we will have the size, of course, and then send it to the cloud to make the inferring, and then get the accuracy back so I can calculate the reward score, which is functional of the size and the accuracy. So the reward will be functional of the size and accuracy, and the state will be the features of the input image. So this is the features of the input image, and here I'm getting the quality factor, which is the action of our agent, which will be only 10 discrete levels. Here I'm gonna explain the AdaCompression algorithm. The AdaCompression algorithm will adaptively switch itself between three main states. which are the inference state and estimation and retraining. Any RL model has its own emulated environment, which is here would be X, which is the input, and M, which will be the cloud model. AdaCompression runs in inference state um, almost all the time. In this state, only the compressed images are uploaded to the cloud to achieve minimum uploading traffic load. To keep stable performance even while the input sensory changes from, for example, from day to night, from indoor to outdoor, the agent will occasionally switch to estimation state with probability B estimate, and meanwhile remains in the inference state with probability 1 minus B estimate. Here it's obvious in the first two steps of the algorithm. In the third step of the algorithm, the epsilon here, it is a feature extractor which has an input of the compressed image as a certain level compression rate C. So the algorithm runs from t equal 1 to k, where here it's create a number of transitions that will be stored in D to create a mini batch which T will train on. So we will have here something called action value function, which will get out which will give to us the optimum compression level. Function will be function of the feature extraction, and after we getting the feature extraction of the last convolution layers, we substitute in another layers another layers that is trainable with parameters of theta. The goal of the training phase is to minimize this loss function. So when minimizing the distance of the action value function and the target yi, the action value function outputs are more accurate estimated for a certain action. During training, some transitions are collected and stored in the it's called exploring the environment. So when I should stop exploring? Here it is different from the conventional the reinforcement learning. The interaction between the agent and the environment are infinite. There is no trigger from the environment telling that an episode has finished. Therefore, they train the RL agent as a manual interval, as here in line 9, of t after a condition of t greater than t stored. That there are enough transitions in the memory so the training phase would start. The RL agent firstly takes some random trials by the episode to observe the environment reaction, and we decrease the randomness with a robust training. So after all the transitions are saved in the buffer D, the agent learn to optimize its action by minimizing the loss function on this selected mini batch. The training procedure will converge as the agent randomness keep decaying. So at the end we will have an agent that have a certain that can select certain actions based on historical optimal experience. In the inference stage, we only upload the compressed image which selected by the agent. But in the estimation stage, we upload both the X reference and the X compressed to calculate the reward, as shown here in this algorithm. The in each epoch I, the transition is stored in the memory buffer. Once the average accuracy of the latest and steps is lower than the average accuracy A node of the earliest and steps in the memory buffer D, it indicates that the current agent is no more suitable for current input sensory. AdaCompression will switch from the estimate to retrain state and call the R training kernel. Otherwise, it will remain in the estimate state with a probability B estimate, or return back to inference with a probability 1 minus B estimate. Therefore, the estimating probability is vital to the whole system. On the other hand, the estimator should be called occasionally to estimate the current agent's accuracy, so to decide if you're gonna retrain or stay in the estimate state in the case of changing the input sensorily of the image. An alternative formulation of the changes of P estimate is to be inverse proportion to the gradient of the accuracy, meaning that when the accuracy is going down, we should increase the P estimate. Why? Because we should increase the chance of the estimated stage more than inference to keep checking the accuracy. After we go from the estimate to the retrain, we should reach a certain threshold of the reward. And after retraining, we should redo the algorithm again, flush our buffer and create new transitions, as the agent already trained need to be tested and need to have different transitions to train on. So here I'm gonna show a figure that simulates the 3 stages. So at this delta on the x-axis, it means that the data has been changed, like there is a change in the sensory. I'm going to show here the 3 stages in the 3 stages, how the transition going between them. As we can see here in the y-x-axis, the delta happens when the change in the accuracy happens due to the change in the sensory. And updating the estimated probability usually happen when the overall accuracy is dropping down. AdaCompression will increase the estimated probability, trying to catch the sensory change. When the overall accuracy is stable and high enough, the estimated probability will decrease again. The estimated AdaCompression start to retrain to adapt the RL agent into the current change in the input images. The retrain steps are shown in this area, and the AdaCompression always use the reference image and the compressed image in the retrain stage. That's why you will see an increase in the uploaded size of the image. Therefore, the accuracy and the probability estimated probability, they will be locked to 1. After finishing retraining, the agent is if the agent in a new sensory in the following iteration, sometimes accuracy decrease accidentally. The estimation probability also will rise more to get more samples, but the accuracy is if the accuracy didn't go uh, low, so it will not hit the retrain phase again. This paper they work with two different data sets, but they didn't work with the total number of samples. They work with 720 samples from this dataset, which they indicated that this is a night dataset, that they have night sensory. And for ImageNet, they work with 2376 images, and they were randomly sampled. Here in the first figure, I'm gonna show different cloud computer services and what is the distribution of each quality factor. We can observe that the quality factor 15 is a more one who has been selected during the inference. The histogram shown in this figure pointed out that for the ImageNet images, the agent prefers lower compression levels, but its choices are distributed more evenly. For the other datasets, which is the MIM images, the agent choices are more accumulated in some relative high compression qualities. Here we gonna compare between the performance in the training and inference, and here is inference only. During the training, you will figure that on the y-axis that y will that it's greater than 1 over in the size overhead. Why? Because as we mentioned before, during the training, we upload the reference image and the compressed image. But after the training, all the sizes become almost 50% lower. So in this figure, we present the compression performance in the inference phase for each cloud service. They tested the AdaCompression on Face++, Polyvision, Amazon. Um, for the solution can reduce the upload. The solution can reduce the upload traffic to around 50%, as you see, while a slight decreasing in the accuracy by almost 7%. GradCam has been used here to present the importance map of deep neural network, and it is done by calculating the gradient of each target and backtracking it to the convolution layer. As you can see here in 1A and 1D, some pictures that the agent chooses to compress highly. The agent selects a lower compression quality on complex textures of the image. On contrast, for the 2A and 2D, the agent chooses higher compression quality to preserve more details, and the agent's interest falls on some smooth regions. Well, I think, I believe that the quality factor here is very low, because when you add more quantization, you give a value for the texture. So I think convolution neural networks are more sensitive for complex textures, and Hinton has pointed to this as the edge information. Here is a source code for the for AdaCompression if someone is interested. Here I have done some experiments for using one of the images in ImageNet, and I use Inception version 3 Ada model. So I compressed the original image to a quality factor of 20, and I was curious to see how the inference, how the rank of the image would change in the output probability. So if you see it with if you put a human to judge what is this image, while it is even quantized using a quantization tables that optimize for human vision, he will not be able to recognize it. But as for a machine, he will able to even to understand this image than the original one, which is more less distorted than this, which by the way will be water snake. So the rank was like 8 and we're using the original image, but now it's 22. That means that the computer, the human vision system is not aligned with the deep learning vision system. And this will raise a very important question, that we should design a codec have the same accuracy of same alignment between the deep learning models and computer vision models. And this is for today. Thank you very much, and you can send me an email regarding the presentation, and enjoy your day. Thank you.